Hey there, folks, back here with another video in our study of vector valued functions. That's getting to be cliche, isn't it, when I start these videos? But I apologize. I'm trying to break these down so that I'm not giving you one big long lecture, but I'm able to give you just little bits and pieces you can watch here and there. That is what they found to be best practices. I did take a class over the summer over best practices for virtual education, and I'm trying to deliver to you here, certainly in class and also with these videos and what I'm doing, that kind of delivery, right? Let's try to incorporate some of these best practices. So, yeah, just trying to make shorter videos, when I can. Certainly some topics just get long, and unless you want part 1, 2, and 3, and no one likes a sequel, so we'll do what we can here. And with that said, I don't have much for you with this one. Let me get into it just to get this over with and get it off to you. But what we are going to do, and I kind of highlighted this with the last video in this sequence, if you're following along, right? If you're playing the home game, and that is the arc length function here, folks. We looked last time in if you're following along in the videos, that is the arc length calculation, determining the length of a vector valued function from point A to point B, right? We looked at that in the last video. What we want to now consider doing, and what we can do, is take that formula seen there for arc length and tweak it a little bit so that it becomes a formula for it becomes a formula that develops what we call the arc length function. Now, why would we want the arc length function? Well, the arc length function is going to lead us to, I realize how many typos I have in here. Is that really a typo? Oh, repeated word. I'm going through. I should clean this up. It was only the only one. All right. Sorry about that. The arc length function is going to allow us to define what's called the arc length parameter. The arc length parameter is going to be important to us when we come back in the next section of material and look at curvature, right? It's going to be important in the respect that we're going to be able to re-parameterize our vector valued function in terms of this arc length parameter, if we have a way to relate it to our generic parameter of a vector valued function. And with that reparameterization, we can look at we can define a concept known as curvature, right? What curvature is the rate of change in the unit tangent vector with respect to length along the curve. Not with respect to any arbitrary parameter t, but with respect to what we know as the arc length parameter. That arc length parameter is going to help us define curvature, right, in the next set of material, so in the next section. So it's going to have its usefulness there. And then later on, we're going to talk about just the idea of what are going to be known as linear integrals. And linear integration, we already are well aware of it, is the idea of single integration, where this single integration that we've been studying has been a very specific case over a line that has always existed along the x-axis from A to B, or has existed along the y-axis from C to D. That integration process can happen actually across a line that is a curve in space, right? Not a classic straight line, but a curve moving through that space. And that integration over that curve doesn't happen with respect to the dimensions of the space, but has to happen with respect to the length parameterization of that space. And that's where S is going to come in. It's going to help us define that parameter of length in n-dimensional space. when our it's going to help us define a unit of length in that n-dimensional space, where x isn't necessarily going to define a unit of length, or y or z isn't going to necessarily define a unit of length. Topic for down the road, chapter 17. It's coming, right? So to begin with, our little tweak here to get this arc length function, where the arc length function, the arc length calculation can be applied in a manner to develop what is called the arc length function for a given vector valued function, where this arc length function gives the functional value for length along a value of r bar of t, starting at a value of t equal to 0 and continuing through some arbitrary value of t, right? This arc length function is defined as follows. It is this description of length that behaves like a function. It is a functional value. It's an output, a dependent value for a scalar measurement, folks, of length, where this output of length depends upon the point on the function. Well, I should say here, depends upon the distance between some starting point at t equal to t null and some ending point at some arbitrary value of t, right? From some starting point on the curve to some arbitrary point at t null, which could be at any point along that curve, there's going to be a length. And we're going to build a function that will tell us that length for any value of arbitrary value at t, right, from some starting position at t null, right? That is what this function is going to give us here. It works a little like that future value calculation, or it works a little like that, future value calculation is how we might want to say it, because it involves a dummy variable here. It is another function that's going to build itself upon the variable of the parameter t. So we're going to reserve that arbitrary t value for the variable of this, and we're going to use u as a dummy variable in it. So it has that dummy variable aspect we're going to see. But what we are going to be given is r bar of t, this vector valued function in n-dimensional space, right? The length along this n-dimensional vector valued function, starting at a particular parameter of t, starting at a particular observed value of t, and continuing off through some arbitrary value of t that is greater than or equal to that observed starting position, right, is given by itself a scalar valued function. And that scalar valued function is defined down below here. It's given by the function s equals s of t, right? Instead of being a function like y equals f of x, we call this function s equals s of t, right? And that defines what we call the arc length function. And how it's calculated is what we see there on the right-hand side. It is this integration, right, that occurs at that observed value, at that starting position of t, and continues up through that arbitrary value of t. That arbitrary value of t is going to play the role of the independent variable in this scalar valued function that gives us the arc length. All right? Depending on what t is, we will get a certain length from this function, but t is going to play the role of the independent variable in this function, s of t. So t is going to come back in as this upper bound, whereas we are going to replace it in our integration with that dummy variable u. And what we integrate in our integrand is actually this quantity here. That quantity is the magnitude, or the length, of what describes the vector given by the first derivative of our vector valued function, r bar. All right? Notice that is the magnitude of r bar prime of u. And we integrate that all with respect to u. All right? We are integrating here. We might take note across the, if we were talking motion in space, the speed. So to figure out this function, this arc length function, and to figure out how far we may have traveled over a given interval of time, we're going to look at how the speed has accumulated over that interval of time, all the infinite speeds that accumulate, and we're going to add those up, right? If we travel constantly at 60 meters per second for, what is that, 30 seconds, right? What is 60 meters a second, a constant rate of change at 30 seconds? Well, it's going to be the product of that, right? It's going to be the sum of all those over that interval, right? And that's going to be given by this magnitude of r bar of u. Some other things we take note of on this is that value of s, that's your arc length parameter. If t is any arbitrary parameter, the value of s in our study is going to stand for the arc length parameter, right? It's a parameter value that stands for a length. We've encountered other parameter values. Certainly t in any vector valued function is just any arbitrary parameter. But if I was to say that was a position with respect to time, all of a sudden that t represents a unit of time, right? So t becomes time, right? Here s becomes a length, right? Similar idea. This s is going to be our arc length parameter, right? And it really is a parameter representing, in a sense, a distance in r sub n, in n-dimensional space. It's going to be what we going to allow us to define distance in an n-dimensional space, where x, y, or z in 3 dimensions don't necessarily define the distance in x, y, or z space. What would be considered a 1 unit length of distance. All right. And then furthermore, what we can say is s, or s of t, is a description of distance with respect to time. And what is distance traveled over time, or the rate of change in distance with respect to change in time? Well, it is speed, right? Or it is this magnitude of r bar prime of t. All right? So we make a note of all that in our definition. And then I do make that connection to speed here. Oh, I thought I did. Maybe I don't. Let's just go ahead and... I laid that out for us verbally. Let's look at our example here, though. Consider finding the arc length function, right, for r bar of t equal to this vector 5 cosine t, 5 sine t, right, over values of t that are greater than or equal to 0. So consider being on this curve, 5 cosine t, 5 sine t, for values of t greater than or equal to 0. Starting at 0 on this curve and then continuing off in a forward direction, right? Well, t might just move forward. And you might be interested, well, what happens if I'm at the point where that parameter t is at 3? How far have I moved along that curve? Well, I can use my arc length function to find that value. I can also just use my arc length calculation, but I can build or prepare a function where I can just substitute in any value of t into that, and it tells me exactly what is that distance traveled. All right? It goes a little further than just calculating an individual arc length, but gives us the description of that arc length for any arbitrary t that happens to fall after our value of t equal to 0 in this case. All right? And we do see here that in this case, the arc length function is given by the scalar function s of t. Right? We've defined this above, which would be equal to this integral seen here, this integral from 0 to t for the magnitude of r bar of u, of r bar prime of u's magnitude, integrated with respect to u. All right, that dummy variable u. The 0 comes from the fact that we are starting to think about this length at the value of t equal to 0 and moving forward. So my value of t null is going to come from this value of 0, right? T, as I've explained above, is going to come into play as the new independent variable in our description of length. that's here going to be dependent upon that parameter t, right? Some value of t greater than or equal to that value is 0. And what we're going to have to integrate across is the magnitude of maybe what we might think of as our descriptions of speed relative with respect to u, that dummy variable, or look at the magnitude of r bar prime of u to u. Now, I went through this rather quick just to get it done in some regards. This is going to require the derivative of r bar of t. That is going to be given by this value here. That would be r bar of u, r bar prime of u. The first derivative of r bar of t would be negative 5 cosine t, negative 5, or positive 5 cosine t. Back up. Long day. Negative 5 sine t, 5 cosine t is this result, right, for the first derivative. So we see this given here in terms of u, that negative 5 sine u, 5 cosine u, is the first derivative of r bar written in terms of u. We're going to want to find its magnitude, which means I'm going to have to take the components of that two-dimensional vector and square them, add those results together, add that sum together, and place it all underneath a square root symbol. That's going to give me the length. Now, I did work this example for a bit of speed because I will tell you these calculations, as with any arc length calculation, are never really simplistic and do have to kind of be set up to be integrable, right? Be able to follow through with the process of integration. But here, what we do notice is I have these two terms with that common factor of 25, where if I factor that out, I will be left with sine squared u plus cosine squared u, where based upon my Pythagorean identity, I know sine squared u plus cosine squared u is all equivalent to the value of 1, and we see that 1 given down below here. That's 25 factored out of sine squared u plus cosine squared u, which has been simplified to 1. So really what we have here is the square root of 25 as our integrand. Well, we know what that is. That's 5. So we're just really integrating from 0 to t, the integrand of 5, all integrated with respect to u. All right? And what is the integral of a constant? Well, with respect to u, that it has a u to the 0 power, so we bump it up to 1 and we divide by 1. So u to the first power, and 5 divided by 1 is still just 5, so it's 5u is our antiderivative. Evaluated from 0 to t gives us 5t. Right? What is 5t? 5t is our description of length traveled along this curve when we have this started at a t value of equal to 0 and ended at some arbitrary value of t. Right? If we start at t equal to 0 and let's say we travel to t equal to 3, we have traveled 15 units along this curve, 15 units of length. 5t gives me that. If t is 3, it'd be 15. If I start at t equal to 0 and I travel to 25 for t, right? I've traveled 125 units of length along this curve, right? My measurement for s in that case would be 125 units, right? 5 times 25, right? It's just simply given by this function s of t equals 5t, right? Thus, for r bar of t, for values of t greater than or equal to 0, right? The arc length function here is s of t equal to 5t, or s equals 5t, right? This is how we relate the length in this two-dimensional system where this vector valued function exists to the arbitrary parameter t that is defining our curve in this system, that is acting as the independent variable in our system, right, for our curve in this system. With That explicit relationship between s and t, though, what we can do is I can solve for one or the other and be able to replace one or the other in respective equations involving these values. I can go from a very arbitrary description, right, for just some arbitrary parameter t, to a very specific description of length, in this case, right, simply by taking my value at t and multiplying it by 5 and getting s. Likewise, I can solve this for t, and given a measurement of length, I can find what would be the arbitrary corresponding parameter t. All right? I make note of that down below here. All right? Note, s equal to 5t implies t is equal to 1/5 s. So everywhere I see that value at t, for instance, in my parameterization of r bar at t as 5 cosine t, 5 sine t, I could consider re-parameterizing that so that we consider position in our space defined not by some just arbitrary parameter, but position in our space along this curve defined by how far we have traveled starting at t equal to 0 and going a certain distance, right? The value given by s. So since s or t equals 1/5 s, from our result that s is equal to 5t here in our calculation of that arc length function, everywhere I see a t in r bar at t, I can replace that with something in terms of s, the independent parameter s, where s is arc length. This value of t gets replaced with s over 5, and this value of t gets replaced with s over 5. T is equal to 1/5 s in the equational relationship here. All right. And I make quick note of what I have already said down below here, folks. All right. What we have done here is, in a sense, given our description of position along this curve relative to how far we have traveled along the curve, as opposed to, right, really as opposed to how far we have just moved in some arbitrary parameter t, right, starting at t equal to 0. Right? How far have we traveled in length from t equal to 0 to some position is thought of as this measurement for s, which might depend upon t, s of t, right? Where we can substitute in, based upon that dependency, the value t, what we might have with regards to s, which would be 1/5 s. All right. With that said, folks, I think I'm going to end there. We're 25 minutes into this video. What I'm going to try to maybe prep up for you here is I got some Mathematica stuff that I still got to put together for you, and I'm going to be working on that. And we might get some illustration of this come out in a Mathematica video that'll be to follow, where we do a little bit more of that vector analysis. I'm going to have some time in the near future to be able to do that, because we are kind of wrapping up with the generic topics here and just getting into the calculations. And if I can take you a little further, a little deeper into these ideas with some of the Mathematica, then we can start to incorporate that. All right. So my hope is to do that for you, and I should have some time here as we wrap up this chapter. We got a little ways till the test over this material. We do have a holiday next Monday, so that cuts a whole half of the week out on us. There'll have to be some independent study during that time, but we are almost through most of the chapter as it is. We really have one section after this to wrap up the chapter, and our test is still a couple of weekends in between now and then. So I have some time in between there to kind of start maybe solidifying this with some more examples in class. Make sure you're attending, and certainly maybe some more lecture videos where we maybe delve a little deeper into some of these ideas, perhaps using Mathematica and whatnot to help out with some visualization. But yeah, we're at 25 minutes exactly right now, so I'm going to cut out of here, folks, and see you in class next time. And we'll be moving on. We'll be looking at curvature soon, getting into principal unit normal vectors and those components of acceleration. Those were a topic that we came back and said, well, we're going to have to come back and talk about these things along with that principal unit normal vector. And that's right around the corner. So see you all then, folks.